4.1. The topic in 4.1 is maximum and minimum values. We've just spent a ton of time learning derivative tools. Now we're going to use those tools to actually apply them to some mathematics. Okay, so I'm going to start this section by drawing a picture of a function. And the important values, x values, are going to be -1, -2, -3, and -4. And in the positive direction, 1, 2, and 3. And here's what our function looks like. It starts with a solid dot above x equal to -4. Goes upwards and makes a hill so that we have the top of the hill at x equals -3. Our function crosses the x-axis at x equals -2. Has a bottom of the hill at x is equal to -1. Pops up and makes a corner at x is equal to 1. Drops down, makes a bowl at x equal to 2. And continues upwards until we have a solid dot at x is equal to 3. Okay, so this is the picture of the function that we're looking at. This is the function y is equal to f of x. Now, when I look at this function, this is a graphical function. I do not have a formula or an equation to describe this function. So all I can really do is rely on the picture. And so one thing that I can say is that the domain of this function is the interval from -4 to +3, and I'm including x equals -4 and x equals +3, and I know that because I have solid dots on my graph, so I want to have square brackets on my domain interval. Okay, so what this section is all about is looking at functions and trying to understand some crucial or interesting aspects about these functions. Okay, and so the things that we're going to look at, the things that we want to describe, we want to be able to describe certain points on y equals f of x. The points that we are interested in, these points, are collectively called extreme values, or you might hear the word extrema. All right, so things that we're going to be interested on with this function are places where we have tops of hills and bottoms of valleys and peaks and maybe high points on the functions and low points in this function. And those points are collectively called extreme values. So I'm going to give you a couple of definitions, and as you're writing down the definitions, I want you to think about how these definitions are the same with each other and how they differ from each other. Because these definitions are going to sound somewhat similar, but they're all a little bit different. So here's our first definition. An absolute maximum occurs at C, C is an x value, occurs at C if f of C is greater than or equal to f of x for all x in the domain. The y value, f of c, is called the maximum value. All right, so on our example over here, we have an absolute maximum, and the absolute maximum occurs at the x value where that c, that x value, where the y value that corresponds to c is greater than or equal to every other possible y value on our graph. So in our case, it looks like the highest point on our graph occurs here when x is equal to 3. And so an absolute maximum occurs at x is equal to 3, and the maximum value is f of 3. All right, our next definition is pretty similar, but instead of an absolute maximum, we're going to talk about an absolute minimum. So an absolute minimum occurs at an x value of c if f of c is less than or equal to f of x for all x in the domain. When this is the case, then we say that f of c is called the minimum value. All right, so in our example, what we're looking for is we're looking for an absolute minimum which is going to occur at an x value where the corresponding y value is the smallest or the least of all the y values that are achieved. So in this case, that means the lowest point on our graph is what we're looking for. So our absolute minimum, in our example, the absolute minimum occurs at, well, the bottom of our goal. So it occurs at x is equal to -1. And the minimum value is f of -1, meaning the y value of the function when x is equal to -1. All right, any questions about that? Questions or comments? So the absolute maximum occurs at the highest place on the graph. It's the x value the location is the x value where our graph is highest. The absolute minimum is the location of the absolute minimum is the x value that corresponds to the lowest place on our graph. Okay? Questions or comments on either of those definitions? Okay? So here's another definition. Actually, I'll write it over there. Our next definition is local maximum. And we say that we have a local maximum, and the local maximum occurs at an x value of c if f of c is greater than or equal to f of x for all x in some open interval containing c. All right. So some of you may be saying, why are you repeating yourself, Diane? It sounds like this is exactly what I just wrote over here for absolute maximum, or for absolute maximum. And so what I want to draw your attention to is that, so the absolute maximum, local maximum occur at C if f of C is greater than or equal to f of x for all x in, and that's where it stops. Over here, for all x in the domain of our function. So that means that we are looking for the place where our function is highest for an absolute maximum. A local maximum, well, local maximum says that as long as there's a little window, for example, at x is equal to -3, if I draw a little interval around there and look at just that interval, then within that little neighborhood around x is equal to -3, the highest point on the function occurs at x is equal to -3. And so we have a local maximum in our example. Local max at x is equal to -3, and the value of the local maximum is whatever the y value is. So is f of -3. We also have a second sort of mini peak over here at x is equal to 1. And so if I look at just a little neighborhood around x is equal to 1, kind of like we had a little neighborhood when we talked about implicit differentiation, in a little neighborhood around the point, our curve past the vertical line test. In a little neighborhood around 1, the highest point on the function occurs at x is equal to 1. And so we have another local maximum at x is equal to 1, and the value of that local max is f of 1. All right, so we have two local maximums. One occurs at x equals -3, one occurs at x is equal to 1. When I look at the picture over here, it's kind of like if you were, imagine that you were walking a hike that had this as your terrain that you were walking across. Well, you would probably start your hike and stop for your first snack at this first viewpoint here. And you take a look around and you'd see that way over here, there's an even higher place, but that's okay. You're semi-satisfied for being at the highest point locally. And then you drop down and you hit a bowl. And then you come up to this little peak over here, and by that time you're really hungry, so you're probably stopping for lunch, and you're going to get some decent views. And even though you see the mountain peak way over here, right in this little neighborhood, in this little local area, this is the highest point. Okay, so these are our local maximums.
Professor, does it always has to be on a rise?
That's a good question. The answer to that is no, and here's the cheesy reason why. Okay, the cheesy reason that we do not always have to have a local maximum on the top of a hill is because of this example. So here's the function y is equal to 3. Pick your favorite x value. Let's say x is equal to 2. When x is equal to 2, within this little interval that we have here, f of 2 is greater than or equal to all corresponding y values within a little neighborhood. And so when I have a constant function, and this is cheesy and it's a little cheating, but it works. When I have a constant function, there is a local maximum at every single x value between -2 and +3. And there's also an absolute maximum at every x value between -2 and +3.
It goes same, it's like bottom, when we, no,
In the negative?
Yeah,
Negative? Sure, I mean, I could have a function that looks like, here's my x-axis, and I have a function way down here at negative 1,000. Every single x value, whether it be x is equal to negative 5 or over here to x is equal to positive 6, every single x value, the corresponding y value is greater than or equal to the y values in a little neighborhood around it.
That would be our maximum.
So still, so in this case here, our local max occurs at every x value between negative 5 and 6, and the value is negative 1,000. The value of the local maximum is negative 1,000.
Okay, so that has a local max, but does that also have absolute max?
So our absolute maximum
It's the same.
has the same greater than or equal to symbol in there. So every single point along this flat line
So,
is the location of an absolute maximum as well as a local maximum.
what about absolute minimum?
So we've defined absolute minimum, and so on this flat line, every single x value is also the location of an absolute minimum as well. So flat lines are kind of dumb.
Yes.
Okay, other questions so far? Okay, so the difference between absolute maximum and local maximum is that the absolute maximum value must be the largest y value, or at least as great as the largest y value across our entire domain. For a local maximum, we need only have some neighborhood around the x value that we're interested in, where then that x value corresponds to the largest or equal to the largest y value on our function. Now there's...
So, I just want to be clear. So, a local maximum can be an absolute maximum too, but it's
Yes.
not vice versa.
So that's exactly true. So local maximums could potentially be absolute maximums. If this hill had gone a little bit higher than this endpoint over here, then our absolute maximum would have occurred at x equals negative 3.
Okay.
On the other hand, an endpoint, I cannot draw an open neighborhood around an endpoint because our function stopped strictly at x equals 3. So because I cannot draw an open neighborhood around x equals 3, we say that there is not a local maximum at an endpoint. Okay. So that is our last comment about our example. We have two local maximums, and there is no local max at x is equal to 3 because x equal to 3 is an endpoint. And at an endpoint, we can't draw a little neighborhood around that endpoint. Okay.
The function went on to infinity, would the absolute maximum be undefined, or would it be infinity?
Yeah, so if this continued to extend forever in our domain, included all real numbers up to infinity, then we would say that this function does not have an absolute maximum.
Professor, this region that you draw at a point, that is like only at that certain point?
So these parentheses here? So I'm looking for an open neighborhood around the point that we're interested in. So open means that I do not include the endpoint, so that's why they're curved parentheses as opposed to square.
But that only corresponds to one certain number. We can have like negative 3 and negative 2, like two elements in that.
From here to here?
Yeah.
So let's say that let's even just say that I went from this point to this point. So let's say negative 2.6 over to negative 1.7. So within this interval, now remember, because these are open intervals, I'm not including that endpoint. So within this interval that I have drawn here, there is no largest y value. within this interval, these largest y values keep getting closer and closer to the y value associated with negative 2.6, but that one's not included. So I can keep getting closer and closer to that, but I don't actually hit it. So there is no largest y value on this open interval right here. Okay, so we've now talked about the local maximum. Write down our final definition, which is our local minimum. We have a local minimum at an x value of c if f of c is less than or equal to f of x for all x in some interval, some open interval, containing c. Alright, so in our example, what we're looking for is places where if I kind of put a little open neighborhood around the x-axis and then look at my corresponding function, then I have within that little neighborhood, I have a lowest point. And so, for example, we have a local minimum at x is equal to negative 1, and the value of that local minimum is the y value, f of negative 1. So we have a local minimum here when x is equal to negative 1. And then we have another sort of mini bowl over here at x is equal to 2. And so we have a second local minimum at x is equal to 2, and the value of that local minimum is f of 2.
So in that case, the first one where you have y equals 3,
Yes.
does that mean your local minimum and your local maximum are the same?
You got it. Yep. Every x value between negative 2 and positive 3 is an x value where there is a local maximum, and an x value where there's also a local minimum.
But not absolute maximum?
And every value between negative 2 and positive 3, including the endpoints, is an x value where there is an absolute maximum as well as an absolute minimum.
Okay. So we probably won't see that again.
So it's good to remember this sort of weird version, but the main ideas that we will see will be places where we really do have locally a bottom of a bowl or the top of a hill. Okay, other questions or comments about these? Some good questions so far. Okay. All right, so as a collection, we talk about the absolute maximum and absolute minimum as the absolute extrema, and we talk about the local max and local min, we call them local extrema. Okay, so extrema is just max and min without clarifying what we're talking about. All right, so the next question that we have is, what can we say about the local extrema of a function f? What can we say about local extrema of a function f? So let's take a look at our picture that we have over here. In this picture over here, I see two places where we have local maximums and two places where we have local minimums. So we've got the top of this hill, and we've got this top of this hill, which is a cusp, and we also have two bottoms of valleys. Okay, so our local extrema are these four circled locations. Now in every single one of these examples, except for one up here, we can say something about the derivative of this function. What do you know about the derivative of this function?
It's continuous. Except for at one.
Okay, so our derivative is continuous, and in particular, what is the value of the derivative at the top of this hill? 0. Yeah, because our tangent line is horizontal, so we have a slope of 0. Same is true down here, as well as at x is equal to 2. So it turns out that any time that we have local extrema, a local maximum or a local minimum, this scenario is going to play out. We are going to have a derivative that's equal to 0, or we're going to have a place where the derivative does not exist. So the answer is if the function f has a local max or local minimum at the x value of c, then either f prime of c is equal to 0 or f prime of c does not exist. And so we want to give a special name to these x values where we have a derivative that's equal to 0 or a derivative that does not exist. So we call these x values critical numbers. So here is another definition for today. Definition of critical number. And so a critical number is a number c in the domain of our function f where f prime of c is equal to 0 or f prime of c does not exist. All right, so in our example here, when I look at this function, the critical numbers on this function, on this particular example, the critical numbers are, well, x equals -3, x equals -1, and x equals 2 are the places where the derivative is equal to 0. And x is equal to 1 is where our derivative does not exist. And so these 4 x values are our critical numbers.
So would that be x equals -3 minus 2 and -1 and x equals 1?
Yes, thank you. That should have a minus. Okay. Other questions about the definition of a critical number?
Wait, is it -3, 2?
All right, what did I do here?
You
Somebody
should
help me
have a
out.
positive 2, right?
+2.
Yeah, so what did I want here? I wanted x equals -3,
Like -1.
x equals
-1.
-1, and x equals +2. That's what happened. I mixed up my 2 and my 1. All right, so if you wrote this down, erase it. Let's try that again. X is equal to -3. X is equal to -1. And x is equal to 2. Yes. Better.
What is that x equals to? That's
And so these are the places where f prime is equal to 0. And this last one over here, x is equal to 1, is a place where f prime does not exist. Okay? And so that occurs right here at our cusp. Okay. Other questions or comments? Okay. So I want to leave you with a thought before you head out. And here's the thought.